Hi guys, welcome to my all-in-one EDEXCEL GCSE 9-1 physics video. I hope you find it super helpful. I'm not sure how long it's going to be, but I have gone through it and tried to make sure I've hit every single specification point. All my perfect answers flash up, and don't forget, if you want to buy my revision guide, which I have written, containing my perfect answers, you can get that on the website, which will flash up now. I hope you find this video super helpful. I hope your studies are going well. Don't forget to come follow me on Insta, Twitter and Facebook, because I add lots of extra exam tips, extra explanations and just general cool science stuff, particularly on Insta. So I really would recommend giving that a go, and I do go through past papers there too. So yeah, hope you find this video helpful. Let's get started.
Okay, new for this specification is the types of energy. They've kind of changed the naming system, so some have stayed the same and some are new. So we're going to go through each of them in turn, talking about what they mean and some examples. So starting with chemical energy, this is to do with energy stores and it's associated with chemical bonds, and really your examples here are things like food. Remember, food is a storage of energy. The same is true for batteries. Kinetic energy, this is to do with moving an object, so anything that has movement has kinetic energy. So a man running down the road, a bus being driven along the street, they both have kinetic energy. Gravitational energy, as the name suggests, is energy associated with an object gaining height. So anything that has been lifted will gain gravitational energy. For example, a chairlift, a ski resort, an aeroplane, these all have gravitational energy, an apple being picked up, for example. Next up, elastic energy. This is the energy stored when an object is stretched, squashed or twisted. Rubber bands are the obvious place here. Catapults, balloons that have been inflated, anything that you distort and then pings back to its original shape will contain elastic energy. Nuclear energy will become very important when we look at nuclear fission, because this is the energy associated with those reactions. So remember the fuel uranium-235, which you do need to know, that is a huge store of nuclear fuel and therefore nuclear energy. Thermal energy, as the name suggests, is to do with heat. Anything that has gone hotter has gained thermal energy, so a hot cup of tea, for example. Magnetic energy is new for you guys, and this is the energy stored when like poles are pushed closer together or when unlike poles are pulled further apart. So like poles, remember, is two south poles being pushed together. Unlike poles would be the north and south pole. So just name any magnets here. So just a simple bar magnet, a fridge magnet that you put on the fridge door. These would all count as magnetic energy stores. And lastly, electrostatic. That's the energy stored when like charges are moved closer together or when unlike charges are pulled further apart. So very similar to the magnetic energy. And your example here is hard, but it's things like clouds. Remember when there are lightning storms? There's a huge build-up of static charge. Van de Graaff generator is the same place. Wherever you build up static charge, you will have electrostatic energy. A hamster of mass 40 grams runs up a 2-meter curtain in 5 seconds. Calculate its power. So we have mass, which I'm going to immediately convert into kilograms to make sure I don't make any errors. So that becomes 0.04 kilograms. We have distance, which is 2 meters. We have time, and we're looking for power. Now there isn't a direct equation that links these components. Now this question is actually more complicated than it looks, because you need quite a few equations, as there's no equation which directly links mass, distance, time and power. First equation we need is weight equals mass times gravity. The next one we need is a formula triangle, which is work done equals force times distance. And the last one contains power, which after all is what we're after, which is work done is power times time. What is the common factor linking the two formula triangles? Well, it is work done. So we need to calculate work done first of all, which is force times distance. Unfortunately, we don't have the force. So we're going to have to work that out, and this relies on you remembering that force and weight have the same unit. So if we work out weight, then we can work out the force. So we need this equation first of all, which is weight is mass times gravity. I've already told you that the mass is 0.04. Gravity on Earth is approximately 10. So therefore the weight is 0.4 newtons. Now we're going to calculate work done using the equation force times distance. Force and weight have the same unit, which is why I can substitute in 0.4 as the force. Distance is 2 as given by the question, so the work done is 0.8 joules. And then finally we can work out power by doing work done over time. Look how I've laid out my answer with all my equal signs lined up, with all my working out shown. So the work done we know is 0.8. I'm only writing it here because I'm running out of space. Divided by time, which is 5. So that becomes 0.16. Don't forget your units for power, which is watts. Right, I'm going to go through some miscellaneous calculations to show how you should be approaching questions if you're not quite sure which equation to use. So my first piece of advice is the moment they tell you to start during your exam, turn over to a blank page and start scribbling out all your formula triangles. So you're pretty much making yourself your own personal formula sheet. Even though that will probably take you about a minute, it will be totally worthwhile because it means when you get to a particular calculation, of which there are many in the physics exam, you don't need to be scrambling around in your brain for the correct one. You just refer to your formula sheet and it should literally just be sitting there waiting for you. So let's have a look at what we have here though. So a student pushes a trolley of weight 150 newtons up a slope of length 20 meters. The slope is 1.2 meters high. Calculate the GPE, so that's the gravitational potential energy of the trolley, and calculate the work done by the student. So what do we have here? Let's identify. Look at the unit. It's a newton, which means it's both weight and force. We know the slope length is 20 meters and we know that it is 1.2 meters high. So gravitational potential energy is given by mass times gravitational field strength times height. We see an immediate issue, which is that we don't have the mass of the object, we only have its weight. So we need to do a preliminary calculation using this formula triangle, which is weight equals mass times gravity. We're looking for mass, so that's going to be weight divided by gravity. Now the weight we've been told is 150 newtons. Gravity on Earth is approximately 10. You could put 9.8, but I'm going to write 10. And therefore you're going to write the mass as being 15 kilograms. Now we're ready to use the original equation. So mass is 15, gravity I've just said is 10. The height, it says that the slope is 1.2 meters high, hence 1.2 is substituted in here. So once I've substituted that in, I get a value which is 180. It's an energy value, so it needs to be in joules. So I've rubbed the rest out so we've got more space. So in B, we're calculating the work done by the student if she pushed the trolley with a force of 11 newtons. So we have work done, we have force. So the formula triangle we need this time is work done equals force times distance. So we're looking for work done. Let's write out the equation. Equals force times distance. The force we know is 11 newtons. The distance, look higher up in the question, she pushed it up a slope of length 20 meters. So that's why we substitute in 20 here. Pop it into the calculator and you know that it is 220. Work done, remember, has the same units as energy, which is why I'm putting 220 joules. Next equation I'm interested in is kinetic energy, which is half of mass times velocity squared. I prefer not to put this into a triangle. I think it's easier if you keep it exactly as it's written, and I'll show you how to calculate the different parts so you can actually see that it can be rearranged easily. In this first question, we're being asked to calculate the kinetic energy of a tennis ball travelling at 46 meters per second with a mass of 500 grams. So as always, write out our equation, which is K is half mv squared. Be careful with your units, because 500 grams isn't in kilograms, so I'm going to put that into kilograms. So remember, 500 grams is 0.5 kilograms. So start substituting in your values. So it's half times 0.5 times 46 squared. So start to simplify. So half of 0.5 is obviously 0.25. 46 times 46, or 46 squared, is 2116. Times that by 0.25, and that gives us a value which is 529. It's an energy value, so it's in joules. Calculate the velocity of a bus travelling through town with a mass of 5,040 kilograms and kinetic energy of, I'm not going to read this number out, of 527,643 joules. So writing out the equation, KE equals half mv squared. We know the KE this time, so I'm just going to pop that in here. I find it easier to answer these questions if I rearrange later. So half of mass, so that's half times 5040. And we're looking for velocity, so we keep that as v squared. The easiest thing now is to work out half of the mass, which is 2,520, times that by v squared. Now we need to get v squared by itself, so the way in which we do that is divide both sides by 2520. So I'm going to do 527,643 divided by 2,520, which gives me a value of 209.382 ... equals v squared, and then we just need to square root to make sure we just get a value for v. So v equals 14.469. Notice I haven't rounded too early. I'm now going to round to 3 sig fig, so it becomes 14.5, and it's a velocity, which means the units meters per second. The diagram shows some electrical appliances. Which appliance is designed to transfer electrical energy to thermal energy? So we're putting in electricity, we're getting heat out of it. It is clearly the kettle, B. Which appliance is designed to transfer electrical energy to kinetic energy? So again, we're putting in electricity, we're getting movement energy out, which would be the food mixer, A. In all appliances, energy is conserved. What is meant by the phrase energy is conserved? And that is that energy cannot be created or destroyed. It is simply converted from one form into another. The lamp has an efficiency of 20%. Explain what this means. And that means that 20% of the energy input has been transferred usefully. So in the case of a food mixer, 20% of the electrical energy in will have been converted to kinetic energy. Or you could have argued that 80% of the energy input has been wasted. Draw a labeled Sankey diagram for the lamp. Okay, so Sankey diagrams always look like this. Now you do find that a lot of it is wasted, so that's why the wasted energy arrow down here will be much broader than the useful energy. And now let's label all of them. So the lamp coming into that will be electrical energy. The useful energy out will obviously be light energy. And then there'll be wasted energy in the form of heat, because do notice that lamps get pretty hot. Because we haven't been given any numbers, you can't add any numbers, so don't worry about that. We now need to look at efficiency. So using this example, a filament bulb was supplied with 80 joules of energy. 10 joules of energy was output as light, the rest was wasted. Calculate the efficiency of the light bulb. You need this equation. So efficiency equals useful energy out over divided by total energy in. And I like to make it a percentage, so times by 100, but that's not altogether necessary. So useful energy out, we know, was the light, so that's 10. Total energy input was 80, times it by 100, so you can pop that into your calculator or just cancel it down like I've just done. So the efficiency is 12.5%.
Now, a resultant force is quite hard to define because there can be lots of forces acting on an object, and a resultant force is kind of the combined effect of all those forces. In terms of the definition you'll need to provide, it is a resultant force is a single force that has the effect of all of the forces acting on an object. In terms of maths and the video we're going to look at now, I'm going to show you how you can work out the resultant force when you've been given several different types of question. Now the issue with the questions isn't actually the maths involved, because actually all you need is a protractor. Make sure you have one of those, and a ruler and a sharp pencil. Make sure you use a pencil in case you screw up so you can rub it out, because if you're using pen you're going to get into quite a mess. And then it's a matter of counting distances, counting the length along your ruler rather than actually using trigonometry to help you solve it. So I promise it's not as hard as it looks. I'm going to show you some examples now. 1. Figures 6 and 7 show examples where two forces act on an object X. In each case, work out the magnitude and direction of the resultant force on X.
Now, don't go straight into drawing a parallelogram of forces because you've learnt that and therefore you're determined to use it. Sometimes you won't need to use it and it won't make sense to. Just look at the figure closely to work out what's going on. So you can see that this guy is pulling on a pulley and he's pulling with a force of 350 newtons. But the crucial thing is that pulley is attached to him, which means his force is actually pulling this weight upwards. Now the weight of the box is pulling the box down by 300 newtons. So what's the difference in those two numbers? Well, it's 50 newtons, and obviously that will be up. So your answer is 50 newtons upwards. Then we've got two men pushing a trolley that's quite a heavy weight up a hill, and so one of them is pulling it. But you can see from these force arrows that they're both pulling in the same direction. So all you have to do here is add together the individual forces. So that's 300 plus 200, and that's a 500 Newton force up the hill. And that's done. Now I'm going to show you when to use the parallelogram of forces. So a force of 3 newtons and a force of 4 newtons act on a point. Determine the magnitude and direction of the resultant of these two forces if the angle between their line of action is. And I probably should have mentioned it before, but magnitude is literally just the size of the force, so the calculation that we literally just did. So in order to do this, you will need your ruler, and you'll need to choose a sensible scale. So I'm going to choose 1 centimetre to represent 1 newton. Doesn't matter which way around you do this, but I'm going to do my 3 newtons along here. So that's going to be a 3 centimetre long line. I'm using a pen, by the way, because obviously I'm not answering an exam paper, so it doesn't actually matter if I screw up here. And then you're using your protractor because you want a perfect 90-degree angle to mark where 90 degrees is, which is here. And now you've got your 2 points. You want to link that together with a, oh that's annoying, it's not actually as long as I want it to be, but I'm fairly sure I've drawn that nice and accurately. So that's a 4 centimetre line going upwards. And now we're going to turn it into a parallelogram. Just going to label my forces. So what is a parallelogram? Well, it's a shape that has 2 parallel sides. So obviously parallel to 3 newtons will be this line. And then parallel to this line, we're going to draw 4 centimetres coming down. Okay, so we've completed our parallelogram, which in this case is just a rectangle. And then in order to find the resultant force, all you have to do is join the corner of that parallelogram to where the forces originated from. We're just going to draw a nice straight line. You must use a ruler for this. And then in terms of working out the magnitude, just measure the length of that line. Yeah, and that's 5. So your resultant force is 5 newtons. And then in terms of working out the direction, you're just going to measure this angle here. And then make sure you're reading the right way. So obviously you're reading, in this case, this way. I think I've done it slightly wonkily, so I'm going to put that as 55 degrees. And that's how I've worked out both the magnitude and direction. Let's do example B. So the same question, a force of 3 newtons and 4 newtons, but this time with a 60-degree angle between them. There's my 3 Newton force again. I'm going to use the protractor to draw, make sure you're using it nice and accurately, a line at 60 degrees. And then we're going to join that up again. And there's the 4 newtons. So let's draw the parallelogram. I'm going to use the protractor to help me improve the accuracy this time. So we're drawing the parallel line that runs against that one, so it's going to run in this angle, but I'm just going to use that to centre it. And we can see this is going to form a nice parallel line. And then it should be straightforward enough to just link these, and it should be 3 centimetres long, which it is. So that's nice. Perfect. And now to work out the resultant force, simply join. Measure the length of this line. The will be error margins, guys, so don't worry too much. That's 6.2 centimetres, that's 6.2 newtons. And then measure this angle here to work out the direction. It's 33 degrees. Time for some moment questions. The diagram shows the apparatus used to investigate moments. The 2 Newton weight is placed 60 centimetres from the pivot. The Newton meter is placed 10 centimetres from the pivot. State the equation linking moment, force and perpendicular distance from the pivot. Right, moment equals force times perpendicular distance. Remember the units. Moments are measured in Newton meters. Force is measured in newtons and perpendicular distance is measured in meters. 2. Calculate the reading on the Newton meter. Ignore the weight of the ruler. Okay, don't stress here. We can work this out. Remember the law, which is that clockwise moment equals anti-clockwise moment. So let's look at the clockwise moment. So we've been told that the weight is 60 centimetres from the pivot. The moment, therefore, clockwise will be 0.6 because you need to convert from centimetres into metres times 2. And now we need to look at the anti-clockwise moment. I can see that this Newton meter is at 10 centimetres. So it's just a matter of substituting them all into the equation and finding the missing value. And I'm going to show you what that looks like. So let's just do clockwise equals anti-clockwise. Please don't run out of space, Hazel. So clockwise was 2 newtons times the distance, which I said was 0.6. We've just seen that the Newton meter is 10 centimetres away from the stand, so that's 0.1, and we're looking for the weight of the ruler, which is the same as the force, so I'm going to write x here, and now we just need to solve. 1.2 equals 0.1x, therefore x equals 12 newtons. Going to chuck in a few other maths things here. So question 6, the person has a suitcase with wheels. The person pulls the suitcase with a horizontal force of 13 newtons for 110 metres. State the equation linking work done, force and distance moved. I don't know if I've told you this before, but try and remember, especially GCSE people, remember all your equations as formula triangles, because then you won't have to learn as much. And then as soon as you get your paper, write them all down on the back, and then you can just keep referring to them, so it won't be so hard to pluck it out of your head. But for the time being, remember work done equals force times distance. So calculate the work done on the suitcase by the person. So let's just write, be good if I had the pencil, work done equals force times distance. Force is 13, distance is 110, and the answer here is 1,430 joules because that is the units. Let's pop it here. How much energy is transferred to the suitcase? Okay, this isn't a trick question. Just remember that work done and energy have the same unit, which is joules, so you can literally just copy that number down here. B, the suitcase falls over. Explain why its gravitational potential energy, it loses gravitational potential energy when it falls. I wondered where the question was there. Remember, you calculate gravitational potential energy by doing mass times gravity times height. Therefore, we know that gravitational potential energy depends on height, so there's your first mark. And therefore, as it falls, h will obviously decrease, and that's all you really need to say. C, the person starts to raise the suitcase again by pulling on the handle with force F. The weight of the suitcase is 150 newtons. State the equation linking moment, force and perpendicular distance. So remember, moment equals force times perpendicular distance. Now we need to calculate the force that the person must apply on the handle to start raising the suitcase. So remember that the clockwise moment equals the anti-clockwise moment. Our clockwise moment this time is the weight of the suitcase pulling downwards. So we're going to write, remember moment is force times distance, so force acting clockwise is 150 times the distance, which is 0.32. We're looking for force, so I'm going to write x here, and then remember moment is force times distance. We've been given the distance, which is 0.87. And then if I solve for x, I get an answer of 55 newtons. This is more maths if you're not happy with how I work that out. Do let me know and I'll add an extra step next time.
We also use moments in gears, and this is when it gets slightly more complicated. So just remember, when we're talking about gears, we're talking about cogs, and you have a large cog and a small cog. Doesn't matter which way around we do it at the moment, but they attach to each other. One spins and it turns the other one, and that's actually what's happening when we change gear, either in a car or on a bike. Now, if you just start with a small cog and you attach it to a big one, as in my diagram here, do you see that as the small cog completes an entire rotation, it will only spun a tiny bit of the large cog, probably about a quarter of that cog, and it will have spun it quite slowly. So we see that when you've got a small cog going to a big cog, and we call that turning into a higher gear, you're going to see that the speed is going to slow down, but you're going to generate a lot of turning effect. If we take the opposite argument, and this time we start with a large cog and we make it attached to a small cog, then clearly as the large cog turns, it's going to cause the small cog to turn pretty much an entire revolution. So that will be spinning the small cog nice and quickly, so we've generated high speed, but we won't have generated a lot of power, and therefore the turning effect will be low. If we take a real life example, let's look at cars. Now, to start a car, you need low speed and you need a high turning effect. And that's why we start in a low gear, which is gear 1. And that's because what you need here is you need a small gear turning into a larger cog, so a small cog turning into a larger cog, so it's turning slowly, but it's generating a lot of driving force, a lot of turning effect. At higher speeds, when you're rampaging along the motorway at 80 miles an hour, you just need high speed. You don't need an awful lot of turning effect because the engine's already got itself to that speed. So this time, you're going to have a large cog attached to a small cog, so that when the large cog turns, it's going to have ensured that that small cog's turned quite a lot. It's turned nice and quickly, hence producing a large amount of speed. So to summarise, a low gear gives a low speed and a high turning effect. A high gear gives a high speed and a low turning effect. If this is sounding absolutely impossible, because it is, just try and learn the notes I'm going to add now and just learn them off by heart, and we'll do some calculations now and make sure you can do that part of the gear topic.
A gear wheel of radius 30 mm is used to turn another gear wheel of radius 10 mm with a force of 60 newtons. Calculate the moment of the force on A, the 10 mm wheel, and B, the 30 mm wheel. So the crucial thing here is to use your equation for calculating moments. So state it, which is moment equals force times perpendicular distance from pivot. And my handwriting is as legible as normal. Now the crucial thing here is to realise that the radius of the gear wheel is the same as the perpendicular distance from the pivot, so you're literally allowed to substitute those values in for each other, and that makes it quite straightforward. So for moment for the 10 mm wheel, you're just going to write moment equals force, which is given as 60 newtons, times the wheel radius, and remember our SI unit for distance is in meters, so you just need to convert 10 millimeters to meters, and that gives you a value which is 0.010 meters. Pop that into your calculator and you'll get a value which is 0.60 Newton meters. Let's do the moment around B. So moment equals 60 times, this time we've got 0.030 meters when we convert 30 millimeters to meters. Pop that into your calculator and you'll get a value which is 1.80 Newton meters.
So we now have our structure of the atom. We know that it has a nucleus containing protons and neutrons. Remember, this is also known as the nucleon number, and that's just the name given to all the particles found within the nucleus. And surrounding the nucleus are the shells of electrons where the electrons orbit. So just to remind ourselves that the mass of a neutron and a proton is 1. A mass of an electron is very small, so 1 divided by 2000 or 1800, depends what your teachers taught you. And that the neutrons, because they're neutral, have no charge, protons have a positive 1 charge, and electrons have a negative 1 charge. Now looking at the periodic table, just remember that the atomic number is the number of protons, and the mass number is the number of protons plus the number of neutrons.
So we're going to start by looking at the various components within a circuit. Then we're going to move on to looking at the graphs, Ohm's law, and I'm going to finish with all the calculations because there's a lot to do on that. But like I said, we're starting with the electrical components. So let's start with drawing a cell first of all. And remember, it has both a negative and positive terminal. The positive terminal is the longer line. If you have two or more cells together, such as this, you have a battery. What's lighting up inside a circuit is known as a lamp or a bulb, and we draw it using this particular symbol. Next up, we need to draw a resistor. This is quite straightforward because it is just a rectangle. Now, if you draw a rectangle, but this time draw an arrow going through it, that tells you it is a variable resistor, which means you can alter its resistance of the circuit. And then underneath, we're going to draw what I call the hockey stick component, and this is a thermistor. It is a temperature-dependent resistor. Looking at diodes now, it looks a bit like the play button. A diode is special because it allows the current to flow in one direction only, given by the direction which the arrow is pointing. This means that the current in this case is moving to the left. If we add a couple of arrows to this, it is a light emitting diode, so that's an LED, and you find those on your remote controls, for example. Next up, if we want to measure the current of a circuit, we're going to use an ammeter. If we're measuring the voltage, we're using a voltmeter. And then we can add a fuse to our circuit. Now remember, a fuse is a safety device. It melts when the current is too high, breaking the circuit. Remember, if you're asked the difference or the advantage of using a circuit breaker as opposed to a fuse, is that a circuit breaker is much faster and easy to reset. Why? Because look at the fuse, the wire is going to melt, and so you're going to have to replace the whole thing before you get your circuit working again. Let's make a couple of notes on how you add various components to a circuit. So I'm just going to draw a simple circuit containing a battery and a light bulb, and now I'm interested in working out the resistance of this circuit. So remember, we're using this formula triangle, VIR. To work out resistance, you just cover the R and have a look at what's left. So it's V over I. I stands for current. It's given by the letter I because it used to stand for intensity of current. So historically speaking, we've always used I to represent it. Now, in order to work out resistance, I therefore need to know both the voltage and the current. It is absolutely essential that you know that the voltmeter is added in parallel around the component in question. That in this case will be the bulb, so you add it as an extra branch, and the ammeter needs added in series, which is why I'm going to pop it here. It doesn't really matter where it goes, but it needs to be in series. They often give you questions with various diagrams asking you what the problem is, and quite often you'll find that the voltmeter and the ammeter aren't in the correct place, so do make sure you know that. Remember, the units for resistance is the ohm, whereas for current it's amps, and for voltage it is volts. Sometimes they want to know why the resistance increases when the temperature increases, and I'm just going to quickly show you why. So if I draw a wire, remember wire is made out of metal, which is made up of positive metal ions and negative electrons. Now what happens if you heat that wire? Obviously those positive ions are going to vibrate more because they contain more kinetic energy, and therefore it's going to impede or inhibit the flow of electrons through the wire. So if they ask you why does resistance increase with increased temperature in a wire, you're going to say it's because the positive ions vibrate more, stopping the flow of electrons. Do notice, however, that thermistors behave differently. As temperature increases, a thermistor's resistance decreases, and that's because it's not actually made out of a metal. You don't need to know why, but do remember that as the temperature increases, the resistance decreases. And while we're talking about resistors, let's look at this resistor, which I've already forgotten to mention, but it's fine. This is a light dependent resistor. Now, when the light levels increase, the resistance decreases, and this is used in your street lighting outside. So as it gets dark, this light dependent resistor, this LDR, is the reason why the lights come on. There are a few graphs I want to talk through now. Now do remember Ohm's law, and that states that the current through a resistor at constant temperature is directly proportional to the potential difference across the resistor. And various components obey Ohm's law and some do not obey Ohm's law. Now a wire obeys Ohm's law, and you'll see that because you can see it's a straight line through the origin. So clearly you can see that as the current increases, the voltage increases, and that's at constant temperature. So a wire obeys Ohm's law. You get a very different shape when you show a filament bulb, so a light bulb. This is not a proportional relationship. We've got a sigmoidal shape, an S shape, and the bulb therefore does not obey Ohm's law because there's no direct relationship between the two. And then lastly, and very strangely, the diode looks like this. Again, it doesn't obey Ohm's law, and the reason it's this shape, the graph, is because the diode only allows current to flow in one direction only. We just need to discuss current and voltage rules for both a series and parallel circuit. So notice that in a series circuit, the current is the same everywhere, whereas the voltage of individual components adds up to the total voltage. And I'm going to show you what that actually means now. So I'm drawing a battery here, which let's say it has 8 volts across it. Then we've got a light bulb here, a regular resistor here, and I'm just going to complete the circuit. So if I tell you that the current here is 12 amps, because I've said that the current is the same everywhere, it doesn't matter if an ammeter got added here, here, or here, all those readings would be 12 amps. However, with the voltage, if you added voltmeters here and here, their readings would not be 8 volts. Let's say that this was 5 volts, the reading. That means that this reading here must be 3 volts, and that's due to that second point, that the voltage of the individual components adds up to the total voltage. The opposite is true in a parallel circuit. Here you find that the voltage is the same everywhere, whereas the current of the individual components adds up to the total current. That means that each of these light bulbs here will have 12 volts going through them, and that explains why with a parallel circuit, how if you keep adding extra bulbs, the brightness remains the same, and that's because they receive the same voltage. However, it will mean that your battery will run out 3 times as quickly as if there was only one. In terms of the current, pretend that was a 2 amp bulb, this was a 2 amp bulb. Well, we know because it has to add up to the total current, this lamp down here is slightly different in that it has a current of 1 amp.
So a 4-volt battery can supply current of 5 amps for 20 minutes before it needs recharging. Calculate how much charge the battery can provide before it needs recharging. At this point, what I always do is I draw out my formula triangles, because why not? It's good to get your head nice and into the question and knowing that you actually know stuff that you can use. So the first one is voltage is current times resistance. The next one is charge is current times time. And then finally, the third electrical triangle that I use is work done is voltage times charge. And just remember that the units of charge are coulombs, so at the end of a question write a capital C, and they're really fussy about how you write the units to make sure it's a capital C rather than a lowercase c in order to get the mark. And remember, I just said that resistance is measured in ohms, and the sign for an ohm is like this, which I've drawn really badly. Anyway, let's look at the question then. Calculate how much charge the battery can provide before it needs recharging. So we're looking for a triangle that has Q in it. So there's 2 of those. And what else have I been told? Well, I've got the current because I've been told 5 amps. And I've been given the time, which is 20 minutes. So what I'm going to use is the QIT triangle. So I'm going to write out, because it's always good practice to do this, Q equals I times T. I is 5. Okay, T is 20 minutes, but remember that's not very scientific, so we're going to convert that into seconds by doing 20 times 60. And the answer here is 6,000. And like I just said, the units of charge are coulombs, so I'm going to write a capital C here. B, each coulomb of charge from the battery can carry 3 joules of energy. Calculate how much work the battery can do before it needs recharging. Okay, so For part B, you're going to use the formula W equals V times Q. V has been given as 4, and Q is something that I just worked out, which is 6,000. So what's 4 times 6,000? Well, it is 24,000. And work done is measured in joules. So there's the answer right there. Okay, let's look at another type of question. Okay, so I've drawn a horrendous circuit here, but hopefully it will still manage to help you at least some way. So this is an example of the sort of thing you could get in the exam. We can see that we have a series circuit with a battery made up of 3 cells, an ammeter with a reading of 0.5 amps and 3 regular resistance in series. We've been given 2 of their resistances, we don't know the third one, and a voltmeter has been added in parallel around resistance number 2. So calculate the total potential difference across the battery. Okay, so all you have to do here, because remember potential difference is the same as voltage, is add up those 3 readings, so that's 2 plus 2 plus 2, which is 6 volts. Nice and straightforward. Okay, work out the total resistance. So it'd be tempting here to try and add up all the resistances of the individual resistors. You can't do that because you don't know the resistance of resistor 3. So we're going to have to do this a different way, and we're going to use this equation triangle. So resistance is V divided by I. The V is 6, which I just worked out. I is 0.5. given by the ammeter, and therefore the answer is 12, and the units are ohms. Okay, finally calculate the resistance of R3. So if we know that the total resistance is 12 ohms, but we've been given R1 and R2, that's 6 ohms, that tells us the difference between those two values will be R3's value. So 12 takes 6 is obviously 6, and that is 6 ohms.
3. The photograph shows an electrical appliance called a toaster. The toaster has a power of 1,800 watts when operating a voltage of 230 volts. State the equation linking power, current and voltage. So I'm going to put my formula triangle nice and out of the way over here. It's PIV, so P at the top, current and voltage in the bottom. So what is the equation? It is power equals current times voltage. Part 2, show that the current in the toaster is about 8 amps. So current equals power divided by voltage. I always write out the equation I'm using. We know that power is 1,800, dividing it by 230 to give 7.83 to 3 sig fig, which is approximately 8 amps. Which fuse rating would be suitable for the toaster? Remember, the fuse rating needs to be slightly higher than that calculated current, and so it's not ideal because 13 is a lot higher, but you can't say 1, 3 or 7. You can't say 7 because it's lower, which means it would constantly have melted when the toaster was in use, which is why D is the correct answer here. B. The toaster uses mains electricity. Mains electricity provides alternating current. Describe the difference between alternating current and direct current. So learn these definitions off by heart. An alternating current is one where the current continuously changes direction, whereas a direct current is one where the current flows in one direction only. The photograph shows an electric heater. The power of the heater is 2,000 watts. The heater is connected to a 230 volts mains supply. State the equation linking power, current and voltage, and I can remember that is PIV. So therefore power equals current times voltage. Calculate the current in the heater, so rearrange so that current is power divided by voltage. Power is 2,000 watts, divide that by 230 volts, and you get an answer which is 8.7 amps. Which of these fuses should be used with the heater? So you're looking for one which is higher and not too high compared with the current you've calculated, and that will have to therefore be 13 amps D because it's the only current higher than the one we've calculated. The two heating elements can be connected in series or parallel. Describe an advantage of each method. So with parallel, the obvious advantage is that you have independent control, so you can turn on and off the heating elements independent of each other, so you could just have one on or both on at the same time. The series one is a bit more of a state the obvious. Here you can use a single switch only to control both heating elements. Some electrical appliances are fitted with an earth wire. Describe how an earth wire acts as a safety feature, and that is worth 4 marks. So state that first of all the earth wire is connected to the metal casing. and that if the casing becomes live, the earth wire provides a low resistance path to obviously the earth. And then you can talk about the use of a fuse which is attached to the earth wire, so that increasing current will cause the fuse to melt, breaking the circuit which cuts off the supply. Explain why this heater should be fitted with an earth wire, and the obvious thing here is because it has a metal casing, and remember metals are good conductors of electricity.
Right, so the topic of static electricity, there's actually not too much to go into with this. Just remember, when you're thinking about static electricity, it's all to do with electrons being transferred from one place to another. So, for example, a polythene rod, which is rubbed with a cloth, will become charged. Why? Because electrons will transfer themselves from the polythene cloth to the rod, so it will become negatively charged. That therefore means it attracts positively charged items, because remember, opposites attract. The questions always go the same, and they'll talk about why does it become charged, and literally the 2 marks you need to specify are, it's the transfer of electrons using friction. And if you actually look at past exam questions, you'll see what I'm talking about. That is so often the answer, I can't even explain. Why does a balloon stick to a wall? Well, you've charged it using friction. The balloon has become negatively charged due to the transfer of electrons, and then it sticks to the wall because it repels those electrons away from the wall, meaning that it can stick to the positive charges. I'm trying to think of other questions, so things like, why do your hairs stand on end when you touch a Van de Graaff generator? That's because all your hairs become negatively charged, they therefore repel, so they stand up on end. Why can't you become charged on a metal slide when you slide down it? Well, that's because metal is a good conductor. So often they'll ask you about metals, things not becoming charged. You just need to say that it's a good conductor so the electrons can freely flow. They like asking you about the uses of static electricity, so something like spraying a bike frame. The way that this works is you give the bike frame a positive charge. You can give the paint all a negative charge, which means the paint repels itself and turns into a fine mist. Then it's attracted to the positive bike frame. One of the advantages of this is, first of all, you get an amazing finish because you get paint in all those hard to reach places. Secondly, you don't waste paint. They may ask you about the inkjet printer, not that I've ever seen a question on that, and in this instance the ink is given a charge. It falls between 2 deflecting plates, and then using electrostatic forces, the 2 plates direct the ink onto the correct places on the paper, and that's how an inkjet printer works. I've never seen a question on that. I wouldn't sweat it if I were you. They may also ask you about a photocopier. Again, I'm yet to see a question. So with a photocopier, what you find is there's a rotating drum which is given a charge, and then an image of the piece of paper you want to copy is projected onto that charged drum. Now the charge drains away everywhere where the ink isn't present, and that means that when you add toner, which is a black ink, it will stick to the charged areas, which is the actual copy that you want. The rest of that toner that isn't needed is removed, and then the paper is rolled between the drum and it's nice and hot, which causes the ink to stick to the paper, and before you know it, a copy of your original paper is formed. One further use of static electricity is an electrostatic precipitator, and that's what they use in factories which produce a lot of polluting smoke full of soot and dust particles. So what happens is the smoke rises through this chimney, it's given a charge, and then there are some plates, that sit at the top of the chimney that the smoke and everything has to pass through, and it's given the opposite charge, meaning that all the soot and dust particles stick to the plate, allowing just the clean air to basically escape through the top of the chimney. Then they knock those plates together occasionally, causing all that dust and sediment to fall down so it can be removed and safely disposed of. They may well ask you, however, about the dangers of static electricity. So that's things like a plane becomes charged when it's flying because of friction between the clouds and the plane. So when it lands and they bring a fuel tanker nice and close in order to refill the plane, you can imagine that a spark could go from the plane to the fuel tanker and cause a massive explosion. So that's a big no-no. So what happens in this instance is the plane is given an earthing strip which is made out of metal, because then that can conduct the excess charge away from the plane to Earth, meaning that there's no risk. Remember that lightning is an example of excess charge draining from the clouds to ground, and that's a good way of adding nitrates to the soil, which is a biology topic to do with the nitrogen cycle. And it's not really a danger, but things like TV screens and computer screens end up being covered in dust because they become charged and they attract little uncharged particles of dust, meaning that the dust covers the computer. So magnetism, well, we're going to start by first of all stating which metals are magnetic. That is iron, steel, cobalt and nickel, and the two most common examples you'll come across are obviously iron and steel. Do notice that steel is an alloy of iron, which means that it contains iron, but it also contains the element carbon. A few basics to point out, which is if you have a bar magnet or any magnet, remember that two north poles will repel, so if you try and push them together, they'll slide past each other. The same is true with south poles, they'll repel as well, and the opposites attract, so a north pole will attract a south pole. Looking at the difference between a soft magnetic material and a hard magnetic material now, the real difference is that a hard magnetic material maintains its magnetism. So steel, for example, is a hard magnetic material. It does not lose its magnetism easily, whereas iron loses it very easily. And to put this into context, if we use a scrap metal yard as our example here, scrap metal yards are full of big old lumps of iron which need moving around. Now you actually use a magnet to move them around, and what you do is you turn on a massive iron electromagnet and it becomes magnetized. It clamps down and picks up that metal that it's trying to move, and then when you've moved it across to the new position, you can basically cut the power source and it will lose its magnetism. You couldn't use steel in this case because you'd effectively find that all that scrap metal would remain stuck to the magnet and you'd never be able to pull it off. So what is a magnetic field line? Well, it's the space around a magnet whereby magnetism can be detected. And in terms of designing experiments whereby you can determine the shape of magnetic field lines, you have two options here. First of all, iron filings, and secondly, using plotting compasses. So what you do is you get a piece of paper, you sprinkle iron filings onto it, and then you place a bar magnet underneath, and you'll see that those iron filings align themselves with the magnetic field. With a plotting compass, instead, you place your bar magnet on a piece of paper, you place a plotting compass near to it, and you make a note of the direction which the arrow on the plotting compass is pointing, and then you pick it up, put it in a new position, keep repeating that process until you've drawn the magnetic field lines. Now just remember that a solenoid is a cylindrical coil of wire. Touching now on the right hand grip rule, so this is just a way of showing the direction of magnetic field lines. So my thumb represents a wire, so in this case it's going from north to south or from up to down, and you might be asked to draw the magnetic field line directions and just follow the direction which your fingers are pointing. Be aware of a uniform magnetic field, and all you'll see here is that the magnetic field lines are evenly spaced and that they're parallel, and those are the 2 points you need to point out with a uniform magnetic field. So how can an object's magnetism be induced? So how can it become magnetic? Well, first of all, you need to start with a magnetic metal such as iron and steel, and then you can place it inside the magnetic field of a permanent magnet, and its magnetism will be created or induced. Obviously, the moment you remove that object, the iron object, from that magnetic field, it will lose its magnetism. Steel, I've already pointed out, is a hard magnetic material, so it will tend to retain its magnetism. So how is a simple electromagnet constructed? And that's simply by connecting a wire to a circuit and running a current through it. How can we increase the strength of the magnetic field of that wire carrying a current? Well, the most basic thing we can do is obviously increase the current, and we can also wrap the wire into a solenoid. So if we coil it up, that will also increase its magnetic field strength. We're now interested in increasing the magnetic field of a solenoid. Because it's already in a coil, what you can do now is add more turns of coil, or you could add an iron ore, which is just like an iron bar which you thread through the middle of the solenoid. You can also increase the current, as I've already specified. We're now looking at the motor effect, which is the part of this topic which people really aren't a fan of. But if I talk you through the overview first of all, and then we'll look a bit more closely about how it all works. So let's start by looking at what the motor effect really is. And all the motor effect is, know that a motor is a piece of wire that spins. So that's what's happening in a motor, a wire is spinning. And we're trying to work out how we can create that, and that is via the motor effect. And you might have seen a simple motor being built at school. So what you have here is you have two permanent magnets. You have a wire in between them which is coiled up, and then that is attached to an electrical circuit so it can carry a current. And the point here is that when the wire carrying the current is placed within this magnetic field of the two permanent bar magnets, you find that there's a phenomenon which we call the motor effect. And what will happen is that wire will start spinning and you have a simple motor. But that's only if you've got a coil of wire placed within the magnetic field of two permanent magnets and it needs to carry a current. And you've probably heard of Fleming's left-hand rule, and that's what I'm going to talk about now. And that's just a way of working out whether the coil moves up on one side or whether it moves down, because obviously it has to move up to begin its spin, then it moves down, moves up, it moves down. So that's what's happening with our motor. So looking at Fleming's left-hand rule, you've got to hold your thumb, forefinger and second finger at right angles to each other. Now the thumb represents the force or the motion, and that will show the direction in which one side of that coil will be moving. So taking the left-hand side, for example, in this instance, it would be moving upwards. The first finger shows the direction of the magnetic field, and remember that the magnetic field always runs from north to south. So based on that diagram you get given in the exam or in your textbook, have a look at those two permanent bar magnets, look at the North Pole, look at the South Pole, and make sure that your first finger matches up with that. Your second finger shows the direction of the current, and on your textbook it should show an arrow showing which way the current's running, if it's running clockwise or anti-clockwise. Just make sure that that finger is lined up there. So once you've lined up your magnetic field, which is your first finger, your current, which is your second finger, you will find that your thumb either points up or it points down. And so it will ask you which direction will the coil move, and you will say upwards or you will say downwards. But just make sure you've got them all in 90-degree planes to each other. My way of remembering what finger stands for what is that the first finger is your magnetic field, first field, second, it contains a C, means that it is showing you the direction of the current. So in terms of answering the 5 markers, which tend to be something like a wire is placed within the magnetic field and a force is felt, discuss. It's worth 5 marks. So it doesn't matter how they word up these questions, the answer is always the same. You want to start by saying the wire carrying the current, so your coil, has a temporary magnetic field, and what that does is it interacts with the permanent magnetic field of the bar magnets. This creates a force causing the wire to turn, and believe it or not, this applies as well when you're talking about a loudspeaker, because anything that moves in and out in this way involving magnets will use the motor effect, even though it doesn't seem particularly obvious. So taking the speaker cone, for example, we start by saying that the wire carrying the current has a temporary magnetic field. This interacts with the permanent magnetic field of the bar magnets found in the speaker. This creates a force, and this force moves the speaker cone upwards, vibrating air particles, causing the sound that reaches your ears. So you're using the same answer here, and honestly, as long as there's a wire moving or the speaker cone moving, your answer remains the same.
The photograph shows a small electric motor. Explain why the coil starts to spin when the switch is closed. Remember, this is a magnetism question, so this is an answer which you can definitely rote learn. So what you want to say is when the switch is closed that the current flows around the circuit. This creates a temporary magnetic field around the magnet, which you can see is near the coil. It's stuck in the coil, so right here is where the magnet is. So this temporary magnetic field interacts with the permanent magnetic field of the magnet, which creates a force, and that force is what is used to turn the coil. And you can mention Fleming's left-hand rule just for an extra mark. Suggest how to make the coil spin in the opposite direction. The obvious thing here is to switch the direction of the current, or you could have swapped the magnets over. Suggest how to make the coil spin more slowly. So how do we weaken that magnetic field? Well, we can reduce the current. You could also reduce the voltage or had a weaker magnetic field, which is harder to quantify. 3A, state what is meant by the term magnetic field line, and that's a line that shows the direction of the magnetic field. The diagram shows a cross-section through a wire placed between 2 magnetic poles, and the wire carries electric current into the page at X. The shape of the magnetic field is shown. Add arrows to any 2 lines to show the direction of the magnetic field. Now remember that it runs from north to south, and we have to do that on at least 2 lines, so I've done 2 there. Draw an arrow on the diagram to show the direction of the force on the wire and label this F. So this is where Fleming's left-hand rule comes in. So remember that your thumb shows the direction of the force, your index finger shows the direction of the magnetic field, and your second finger shows the current. So make sure you're holding your left hand up here. Make sure that your second finger is pointing downwards at X. Then line it up so that your first finger is pointing north to south. And then when you've done this, you'll see that your thumb is pointing to the right. And remember, that shows the force, which is why it's in this direction. Now we need to describe the magnetic field in the region shown inside the dotted square. So if you have a look at that, you can see that first of all, the magnetic field isn't uniform because the lines are differing spaces apart. And also notice that they're flowing in the same direction, so they are parallel to each other.
Figure 21 shows how small weight placed on the insulating bar makes the y-axis go back and balance in its original position. The y-axis is 5 centimeters long and carries a current of 1.5 amps. The small weight causes a clockwise moment of 4.8 times 10 to the minus 4 Newton meters. Calculate the magnetic flux density where y-axis is positioned. Give the unit. First of all, it is essential that you have everything in the correct units. So we got told that was 8 centimeters. We need to convert that to meters, so just do 8 divided by 100 to do that, which gives you 0.08 meters. We've been told the moment, so we need to work out the force. So moment equals force times distance. We know the moment is 4.8 times 10 to the minus 4, so we know that equals F times 0.08, which I've just worked out. So to find F, you're going to do 4.8 times 10 to the minus 4 divided by 0.08. And that gives a force which is 6 times 10 to the minus 3 newtons. The reason why we need this is we're now going to pluck that equation out that we need to work out that magnetic flux. So that's going to be force equals magnetic flux density, I'm going to write it like this, otherwise I'll run out of space, times current, which is given by I, times length. So I've just worked out the forces, 6 times 10 to the minus 3. We're looking for the magnetic flux, so I'm going to put an X there. We've got the current, which we've been told is 1.5 amps. And lastly, we got told that the wire is 5 centimeters long, so I'm going to convert that to meters again by dividing by 100 to get 0.05. Let's just cancel some of this down. So 6 times 10 to the minus 3 equals 0.05 times 1.5, which is 0.075x. To get x by itself, you need to divide both sides by 0.075. So that is 6 times 10 to the minus 3 divided by 0.075, which gives you a value of 0.08. And the unit for magnetic flux density is the Tesla, or capital T.
Now we're going to look at electromagnetic induction, or basically how voltage or current may be induced. It's a very similar concept, we just need to look at it from a slightly different angle. So I hope you realise that with your force and your magnetic field and your current, it's a bit like a physics formula triangle, which is that if you put in magnetic field and you put in current, then you get force. So it makes sense, therefore, that if you put in the force, you put in the magnetic field, then you should be able to make current. And indeed, that's what electromagnetic induction is all about. If a wire is moved into a magnetic field at right angles, then you find that a voltage will be induced. And if it's connected up to a complete circuit, that's where your current comes from. Do notice that you must move the wire or the magnets, it doesn't matter which way around you do it, but you must move them at 90 degrees to each other. If they're parallel, then you won't induce your voltage. Now, in terms of working out which direction everything's going to move in, this time you use Fleming's right-hand rule. So you find again that the thumb shows the direction of the force or the motion. First finger is the magnetic field, second finger is the current, but you have to use your right hand because otherwise it won't line up properly if you use your left hand. And this is really how a simple generator works, because if you're creating current, then Clearly you could make electricity from that, and all a generator is a machine which creates electricity. So how could you increase the size of that induced current? Well, clearly you could use stronger magnets, you could have a stronger magnetic field, you could move the wire more quickly, and you could wrap the wire into a coil. Looking at the use of generators in everyday life, you can use the example of a bicycle dynamo. And just to explain what this is, so some bikes, I don't know if you've ever used the Boris bikes in London or any of those bikes you can rent in other countries. I don't know if you've ever cycled them in the night time, but they have lights, and it's not because they have batteries that need replacing, it's because they contain simple dynamos which uses your motion of pedaling the bike to actually power the lights. So we need to explain from an electromagnet point of view how that works. So as you turn your pedals, clearly the bicycle wheel turns. This turns a magnet which is located within a coil, and this magnetic field of the magnet cuts the surrounding coil, which induces a current. So within a bicycle dynamo, you find that there is indeed a simple generator.
Diagram 1 shows some of the apparatus used to investigate the force on a current carrying wire XY in a magnetic field. Diagram 2 shows the poles of the magnet viewed above. Draw the uniform magnetic field between the poles. Okay, this isn't as hard as it might sound. You just need to draw straight lines, so use a ruler. I'm not using a ruler because I'm using the iPad. And you need to do a minimum of 3, and then obviously the magnetic field goes from north to south, so add arrows showing that, and that is more than enough. The current carrying wire XY is at right angles to the magnetic field. The current in the wire is 10 amps. Suggest why the wire used in this investigation must be thick. Any sensible suggestion? So otherwise a large heat might cause it to melt if it was too thin, or you could say a thicker wire is used to reduce the resistance, or you could say that it doesn't, so that it doesn't sag or bend. Explain why the wire XY experiences a force when there is a current in the circuit. So have another look here. This is quite hard, but just say that the magnetic field of the wire interacts with the magnetic field of the two magnets, and you actually get a mark for just mentioning Fleming's left-hand rule. These questions are strange with electromagnets. Just kind of write down everything you know, even if you're worried about whether it actually fits the context of the question. State 2 ways in which this force may be reduced. Okay, you could reduce the current, or you could use less powerful magnets. The photographs show how an electric toothbrush fits on its charger. The charger and the toothbrush each have a coil of wire inside them. The diagram shows how the two coils are linked by a U-shaped core. This arrangement of core and coil acts as a transformer that reduces voltage. Name the type of transformer that reduces voltage. Well, that would be a step-down transformer. Explain why the core is made of a soft magnetic material such as iron. Remember, it's because iron is softly magnetizing, and therefore it loses its magnetism easily, and also you need to state the fact that the magnetic field in the core can change. State the equation linking the input primary and output secondary voltages and the turns ratio of a transformer. This is something you're just going to have to learn. So write input voltage divided by output voltage equals primary turns divided by secondary turns. Please just learn that off by heart. The transformer has 520 primary turns and 30 secondary turns. The input voltage to the transformer is 44 volts. Calculate the output voltage. So let's just substitute those numbers in. So that calculation will look like this. The input voltage is 44. We're looking at the output, so I'm going to put X here. Primary turns is 520. Secondary is 30. It's up to you what maths you want to use to do this. What I tend to do is flip the whole lot, so it becomes X over 44 equals 30 over 520. And then all you need to do is use your calculator to do 30 divided by 520 and then times it by 44 to get X by itself, and X will equal 2.5 volts. The diagram shows parts of a transformer. The input voltage to the transformer is 230 volts, the output is 25, there are 100 turns on the secondary coil. Name the type of transformer shown in the diagram. Well, it's a step down because the output voltage is lower, so write step down there. State the equation linking input primary voltage, output secondary voltage, primary turns and secondary turns. You really need to learn all these equations. So this is what the equation is. Remember that it's input primary voltage over output, which is secondary voltage, equals number of primary turns divided by secondary turns. So now we're calculating the number of turns on the primary coil, so I'm going to be using that equation, and X is therefore NP here. And then let's substitute what we know. We know that there are 100 turns on the secondary coil. Oh my gosh, the gardeners are so noisy. And then on the output of the transformer, we've got 25 volts, so that's voltage on the secondary. And then if you scroll up, you'll see that the input voltage in the primary side is 230, and now you need to solve that for X. So just do 230 divided by 25, times it by 100, and you'll have 920 turns. B. Explain how transformer works. In your answer, you should include the reasons for using two coils, the iron core and alternating supply. Don't stress too much if you're like, oh, I don't know how to crowbar those things into my answer. Just write what you would write normally and you'll find that they'll just fit in. So first of all, say that transformer either steps up or steps down the voltage. Say that the current in the primary coil produces a magnetic field. For the third mark, say that this current is changing, which causes a changing magnetic field in the core. You need to say that the core strengthens the magnetic field. Then state that the field lines interact with the secondary coil and that this induces a voltage in the secondary coil. If you think I said that quite fast, just rewind this video and listen again. But you do need to learn all the steps. It's a nightmare and I hate magnets too. You're not alone.
So when we look at solids, liquids and gases, be prepared to draw their particle diagrams. Notice that solids have particles which are in very fixed arrangements, and that's because the particles vibrate around in fixed positions, they have little kinetic energy, and there are strong forces between them. Moving to liquids, you see that the particles are slightly more widely spaced apart, they're not touching quite as much, so they have intermediate forces between them, and they vibrate more, and they don't have fixed positions. Gases now, so you need your particles to be further apart. This is because they have large amounts of kinetic energy. Obviously they're not held in fixed position and there are weak forces between the particles, and here's your summary now. Let's start naming the correct conversions between all these various states of matter. So remember, if you're going from a solid to a liquid, that is melting, like a solid ice block turns into water, melting. If you go the other way and the water turns into ice, clearly that will be freezing. If you have a liquid and it turns into a gas, that will be boiling or evaporating. And then when you have a gas and it turns back into a liquid, that is condensation. So that's what happens when you have a shower and you see it getting all misted up on the windows. Condensation is occurring here. Touching slightly more on evaporation, so how does the evaporation of a puddle or any liquid happen really? So what you find is that the particles have differing kinetic energy. Now those particles with the most amount of energy will evaporate first and they will leave the surface of the liquid. And what will happen is it will mean that the remaining particles have lower average kinetic energy. Do notice that in a closed container, condensation and evaporation will be occurring simultaneously, which means at the same time. More definitions now. Clearly the melting point of a substance is the temperature at which a substance melts, the boiling point, the temperature at which it boils, etc. Now the key thing to remember here is that if you have a pure substance, and that's a substance with no other impurities at all, what happens is that when it changes state, its temperature stays the same the entire time while it is changing state. So it's not like the first few molecules start boiling and therefore the temperature changes. No, while the whole substance is taking its time to boil, the temperature will be the same. So in the case of water, that'll be 100 degrees Celsius. And that's why you get the very characteristic graph when you're looking at the melting and boiling of water, for example. So it'll go up and then it will level out. That's while the water is melting, then it'll go up again, and then you get a very straight line again for quite a long time, and that's when the water is boiling. Another definition is latent heat, and that's the energy transferred to a substance whilst it changes state. Now we get even more dull and we start talking about internal energy, and this is the energy stored by particles in a substance, and it's made up of the total of two things. It's the total of the kinetic energy of the particles and the potential energy of the particles, which is due to the relative positions they are found from each other. You may be asked to use the specific heat equation, and that's all to do with calculating the energy of the substance. It's fairly straightforward. The equation here though is E, so that's change in energy, equals mass times specific heat capacity times temperature change. So they could give you an experiment where they're heating some water. So the way you'd calculate the energy change of the water is you'd get the mass of the water, for example 100 grams, you times it by its specific heat capacity, which is actually just a very specific number, and then times it by the temperature change given in the question, and then you substitute all those numbers in and you'll get an energy change, which therefore will be given in joules. I'm trying to think of exam type questions they may ask you. They may ask you about how puddles evaporate on a hot day, or how water boils, and you're just going to say that the particles gain kinetic energy, and those particles which gain the most kinetic energy will escape first, and they'll escape from the surface of the liquid. And because they've escaped, it means that the remaining particles have lower average kinetic energy, and that's the sort of answer you need to rote learn, and I've seen it come up lots of times in various examples, so I think it's sensible learning that. Another terrible definition is the definition for the specific latent heat of fusion, and that's the energy needed to change 1 kilogram of a substance from a solid to a liquid. The specific latent heat of fusion is given by the equation energy divided by mass. Now the specific latent heat of vaporization is the amount of energy required to change 1 kilogram of a liquid to a gas, and the equation for calculating that is very similar to the one I've just mentioned. And you need to be able to describe what pressure is in terms of particles. So taking particles within a crisp packet, or within a container, or within a squirty cream container, just remember that those air particles collide with the walls of the container. No! What are you doing? Lyra? No, no claws, no claws. No claws. No claws. Should get rid of this. Please be good. Be good. She always meows when I talk to her, and she knows she's being naughty. Lyra! So, those particles collide with the walls of the container, creating a small force, and that force given over a specific area is the pressure, and we know this because of the equation pressure equals force over area, so you can use the triangle FAP to help you remember that. Do be prepared to provide an answer as to what pressure is, or how pressure is produced within a container, as that could be worth 4 marks. And do remember those particles within the container have random movement because they are air particles and they are a gas. Why does that pressure increase with increased temperature? Well, clearly increased temperature provides those particles with greater kinetic energy, which means they collide with the walls of the container both more frequently and with greater force, hence you see an increase in the pressure. So if we go the opposite way and we decrease the temperature, clearly decreasing the temperature will decrease the kinetic energy. Eventually the particles will have no kinetic energy whatsoever, and at this point we say that absolute zero has been reached. Because the particles have no kinetic energy, there is no pressure. It has a value which is minus 273 degrees Celsius, and if we're using the Kelvin cycle, which is a different scale for measuring temperature, so we are used to dealing with Celsius, however the Kelvin is also a very good system, and we say that absolute zero is 0 Kelvin. So be able to convert between the two scales, so minus 273 degrees Celsius is 0 Kelvin. So in order to convert between the two, to get from Kelvin to degrees Celsius, you want to minus 273. And to get from degrees Celsius to Kelvin, you want to add 273. So let's take an example, 20 degrees Celsius. What is that in Kelvin? It is 293 Kelvin because we've added 273. So we're looking now at the density and pressure topic. So remember, density is to do with how close together particles are. Heavy objects have high density, and that's because the particles are close together. Lighter objects are less dense, and that's due to the further apart spacing of the particles. Now the equation you need to know about is density equals mass over volume. Now I use a formula triangle as usual to remember this, and one of my tutees taught me a good way to know this is drunk men vomit. So you want D at the bottom of the triangle, M at the top, V at the bottom. So to work out density, it's mass over volume. Mass is density times volume, and volume is mass divided by density. They're quite interested in you being able to determine the density of various objects. So let's start with symmetrical objects, things that we can easily measure the volume of, so things like cubes, cuboids, brick, for example. Now what you want to do here is, obviously looking at the equation density equals mass over volume, you want to measure the object's mass using a top-pound balance and get that measurement in kilograms. Then to measure the volume, we simply use a ruler. We measure the length, width and height, multiply those values together to work out the volume, substitute in your mass and volume values into the equation, and out pops the density. Now it's going to be far more difficult measuring the density of an asymmetric object, something like an ornament or a vase or a stone, and that's because you can't easily measure the length, width and height of the object, so it's very difficult to determine its volume. This time we're going to use the displacement method. The simplest way to describe this is you fill a measuring cylinder with water, you measure the volume, then you add the object to that measuring cylinder and you measure the new volume, and the difference between those two values will clearly be the volume of the object, so its volume is now sorted. Its mass is easy to determine using the top-pound balance method. Substitute the values into the equation, so make sure you state the equation in your answer, that will be worth a mark, and out pops density. Now pressure, so pressure is acting all around us. Remember that pressure around atmospheric level is 100,000 pascals or 100 kPa, and that pressure increases underwater. And if anyone goes scuba diving, you'll know this when you have to do your training, you need to be aware of the pressure around you. And the reason the pressure increases is simply because there's more water above you, the atmosphere above that, and it's all bearing down on you, hence you experience a higher pressure. At the top of mountains, you'll have less pressure, and that's simply because there's less air above you. Now, in terms of when you go up in an aeroplane, just to try and give you some context, has anyone ever noticed that you get bread rolls in those little plastic packets or a packet of crisps, and it looks like a pillow in an aeroplane? You get super puffy, and that's because when the packet of crisps, for example, was sealed at ground level, then you have the atmospheric pressure around, so that gets sealed into the packet. And so you've got those particles colliding, creating pressure against the walls of those crisp packets. However, when you go into an airplane and you're at altitude, then what you find is the surrounding air, there's less pressure. So you find there's more pressure within the crisp packet, less pressure surrounding it, which is why it puffs out.
Here I'm looking at a question, so which exerts more pressure on the ground, a tank with a weight of 80,000 newtons or a cyclist with a weight of 1,000 newton? The tank tracks have a contact area of 10 metres squared, and each of the cyclist tyres have a contact area of 0.6 metres squared. So what you need to do is begin by drawing the triangle to help you sort out your formula. So it looks like this: forces at the top, then it goes area, and then it goes pressure. So I'm going to change to black. So I'm obviously looking at the pressure, so I need the form of the equation, which looks like this: force over area. I'm going to start by looking at the tank. So its pressure will be its force, and obviously that will be the 80,000 newtons. Why? Because weight and force have the same units, so that is newtons, and therefore we can use them interchangeably. So that's 80,000 divided by the area, which I've been told is 10. And here's the answer, 8,000 newtons per metre squared. Now let's look at the cyclist. Okay, so the pressure will equal the force again, which is this time 1,000 newtons, divided by the area. Now don't make a mistake here. The area is 2 lots of 0.006. The reason being because obviously the cyclist has 2 tyres. So I'm going to do 0.06 times 2, which equals 1,000. Please don't let me run out of space. By 0.012. I'm going to use the calculator here. And the answer here is 833 newtons meters squared. So, as you can see, it's obvious that the cyclist exerts more pressure because their pressure is 83,333. So make sure you write that the cyclist is the answer. I'm going to show you some more density questions.
because I've touched on this density triangle, which I told you is drunk men vomit here, but there's another equation you need to be aware of with density, which I'm going to bring up now because I found this particular example so I could talk about it. So question 6, this question is about pressure in a liquid. The teacher uses this apparatus to demonstrate pressure difference in water. The apparatus is hollow and has 3 short tubes at different depths. The teacher completely fills the apparatus with water and water comes out of all the tubes. So look, path of the water from the top of the tube. State the relationship between pressure difference, height, density and G. So I wouldn't use a triangle here, you do just need to learn this. And it is pressure difference equals height times density times G. That does not look like a G. Don't know why I can't do that times properly. The diagram shows the path of water coming from the top tube. Complete the diagram by drawing the paths of water you would expect to see from the other tubes. Now notice that this question exists. I have a lot of people I teach that probably wouldn't even have spotted that that was a question and would have lost 2 marks immediately. So do make sure you read every single question and that you indeed attempt every question. Now I already told you that the lower down you go in water, so the further under the ocean, the same is the case here, the greater the pressure that is experienced. That means that the path of water coming out of the lowest pipe will have travelled the furthest due to that increased pressure. So we're looking at something like this. And then for the middle tube, you're looking for an intermediate path. So like that. Explain the pattern of the paths of water from the tubes. So I've accidentally already alluded to this. You want to say that the water at the bottom of the tube has greater pressure and therefore the force acting on it is the greatest, meaning that it travels furthest. In another demonstration, the teacher uses this container. The container is made of glass and each section has a different shape. The teacher pours water into the container until it reaches the level shown in the left-hand section. Complete the diagram by drawing the water levels in the other 4 sections. So this is probably quite a hard question, so just be aware that the air pressure is the same for all vases, after all they are connected. And that means that the water level will be the same for each regardless of the shape. Make sure you actually draw within the vase. I have a habit of drawing outside of the vase. So I'm going to use in the exam a ruler to show that it is constant for each vessel. Explain why the water fills the container in the way you have shown. So we need to describe why we've drawn it at that constant level. Well, I've already said that the air pressure is the same for all, so that's worth 1 mark. We know that it's water. We know we haven't changed liquids throughout. Therefore, the density of the liquid will remain the same. And then look at how that equation links. So pressure difference equals height times density times G. Gravity hasn't changed, density hasn't changed, pressure hasn't changed. Therefore, height won't change, hence the same height for each. And lastly, you could point out that the vessels are connected. Question 4. A diver works in the sea on a day when the atmospheric pressure is 101 kilopascals and the density of the seawater is 1028 kg per m cubed. The diver uses compressed air to breathe underwater. 1,700 litres of air from the atmosphere is compressed into a 12-litre gas cylinder. The compressed air quickly cools to its original temperature. Calculate the pressure of the air in the cylinder. The only reason these questions are hard is because you need to actually pull out the information in the question, but once you've done that, it's straightforward enough. So what numbers have we been given? Well, we've been given atmospheric pressure of 101 kPa, density, which is here, but I don't think we need to use that quite yet. We've been told that 1,700 litres of air is compressed into a 12-litre gas cylinder. So we can see here straight away we've got 2 volumes, we've got a pressure, and we've got another pressure. So which equation contains 2 lots of volumes and 2 lots of pressures? Well, it's this one. Correct me if I'm wrong, but I think this is given on the front of your paper, but it's quite straightforward to remember anyway. Just make sure your units are all the same and then start subbing in these numbers. So pressure 1 is going to be 101 times volume 1, which is 1,700, equals, we're looking for P2, so we'll keep that there, times 12. And then the way to work this out is work out the left-hand side first of all. So 101 times 1,700. And then divide both sides by 12. And then when you round that to 3 sig fig, you're going to get P2 equals 14300. The units will be kilopascals.
State the equation linking pressure difference, depth, density and G. So you can write this out in words. You can literally write pressure difference equals depth times density times G. Or you can write it out as symbols, which would be P equals H times, remember it's the Greek letter rho, which looks like a P, so that's why it's a bit confusing, times G. So if in doubt, I would write it out in words. Whatever you do, don't write gravity for G. They're very fussy over this. You need to write acceleration due to gravity. Calculate the increase in pressure when the diver descends from the surface to a depth of 11 meters. So what you're going to do here, I'm just going to write out the equation. So pressure equals height times density rho times G. So 11 times density, which we were given right at the beginning of the question, which is 1028 times G, which is 10, and we need to know that number. You can use 9.8 also, but 10 is easy. And then you work that out and you get an answer which is 110 kPa. Part 3, calculate the total pressure on the diver at a depth of 11 meters. Assume that the atmospheric pressure remains 101 kPa. Well, because it's worth only 1 mark, they've only given you a small gap. You shouldn't be doing any proper calculations here, so no substituting into equations. You simply need to add together your previous value to the atmospheric pressure. So that's 101 plus 110, which equals 211 kilopascals. C. As the diver breathes out, bubbles of gas are released and rise to the surface. The bubbles increase in volume as they rise. Explain this increase in volume, 2 marks. Make 2 separate points. One of the most basic arguments you can make here is that it will be warmer closer to the surface of the sea because you're closer to the sun. That would be worth 1 mark. And what that does, because remember, if it's warmer, the particles vibrate more, and therefore the pressure will increase inside the bubble, which leads to its volume increasing. Or you could give an argument to do with the fact that pressure decreases closer to the surface. Always provide an equation in this case, so that would be pressure equals height times density times G. And then you would state that the PV value is constant for a fixed mass of gas. And if that sounds weird, you can state the other pressure equation once again, which is P1 times V1 equals P2 times V2. The diagram shows some gas particles in a container. The piston can be moved in or out to change the volume of the gas. Add arrows to the diagram to show the random motion of the gas particles. Just literally show them just moving around really randomly. Just make sure you add enough arrows. They're just a gas, so it's quite straightforward. Explain how the motion of the gas particles produces the pressure inside the container. This is an answer you can rote learn. So you want to first of all talk about the fact that gas particles have random motion and that they collide with the walls of the container. Then this creates a force, and then lastly state an equation, which is pressure equals force over area. And that is the easiest way in which you'll get 3 marks. I would really recommend you learn that answer off by heart. State what would happen to the pressure if you push the piston into the container without changing the temperature. Well, you've got a smaller volume, so therefore the pressure would increase. When the gas in the container is heated, the piston moves outwards. Place ticks against the 3 correct statements. The gas particles get bigger. No, that's not true. The mass of gas particles stays the same. Yeah, that makes sense. The gas particles move faster. Well, clearly, if you heat them, they're going to gain kinetic energy, so they will move faster. The average distance between the gas particles increases. Again, true, because if they're moving faster, they'll be moving away from each other, therefore increasing the distance. The temperature of the gas decreases. Well, no, the container's been heated, so that's absolute rubbish.
So I want to quickly talk to you about Hooke's law. Now, Hooke's law is a pretty boring experiment whereby a guy called Hooke, amazingly, originally hung various weights off a spring and measured the new length of the spring. And then obviously as more weights were added, the spring got longer. And then he plotted a graph which was force, and it's okay to plot force because remember force and weight have the same unit, which is newtons, against the extension. And you see on the graph that it should be a proportional relationship, which means that as the weight increases, the length of the spring increases, which makes sense. Then you'll find that the line distorts, and that's because we're no longer increasing proportionally, and that's because the elastic limit of the spring has been reached. it's deformed, it's bent out of shape, and it won't return to its original length. So that's what underpins Hooke's law. Now we're going to look at a past exam question on it. So a student investigates whether a spring obeys Hooke's law. She uses the apparatus shown in the photograph. Which additional measuring instrument does the student need for the investigation? Well, I've told you it's all about measuring the length of the spring, so we need a ruler. Explain how the student can investigate whether the spring obeys Hooke's law. So we're basically looking for experimental details on what they're going to do. So first of all, you want to measure the original length of the spring using that meter ruler, and then we're going to add a known weight to that hook and measure the new length of the spring. And then we just repeat the process using a range of different weights. So we could go up to 20 newtons, 30 newtons, 40 newtons, or we could repeat at each weight, because remember, repeating, calculating an average is really important, and that's worth a mark for just pointing out that particular experimental detail.
Thank you so much for watching my video. Well done if you made it to the end. Don't forget you can buy my Science with Hazel Perfect Answer revision guides on my website. They're available right now at www.sciencewithhazel.co.uk.